So, hi everyone. So, we'll start about 5 minutes after this. So, let other students join and then we'll start. Everything is listening. So we'll start now, and maybe other students will join later. So, welcome to the last session of this course, that is the problem solving session, the summary session. I have been teaching for the last 8 weeks, and I'll summarize the total contents in this session. So the course is titled as Sensor Technologies, Physics, Fabrication, and Circuits, and my name is Shona Bhattacharjee. So there is more details about me. So as I have told, my name is Sonam Bhattacharjee. I have been pursuing my PhD in the Department of Electrical Engineering, Indian Institute of Technology, Jodhpur. My research interests are around the fields of flexible and organic transistors for neuromorphic computing. So this sensor kind of a thing is very near to me. These things. I have completed my bachelor's with honors in physics from Calcutta University. After that, I pursued like MSc in electronics. And to know more details about me, you can go to this website of mine. And also to connect with me, you can visit the social media link. So our course was divided into eight fractals, out of which the first two fractals were for basics of sensors, the introduction parts, and then the parameters. After that, the next three fractals were for physics of sensors. Those were of capacitive and thermal for the first class. Then the second one was for chemical and impedimetric. Then the last one was for optical and magnetic. After that, the next two subsequent classes were for fabrication and characterization, where we have learned the deposition techniques and how to pattern desired pattern on our sensor. And the final fractal was sensor systems and circuits. How to integrate our fabricated sensor to a circuit. So, as like you can see, the um, total course was divided into like which kind of a sensor do we need, how to characterize the sensors, if the sensor is perfect for our use case or not, these kind of a things. Then we have learned different types of sensors, like different if it is a capacitive sensor, if it works in the impedance region, or it works on the on basis of like optical intensity or light intensity based sensors. So this kind of a things. After that, we have learned how to fabricate this kind of a sensors, and then characterize the sensors for specific patterns and those things, like using lithography or maybe using ALD techniques and those things. After that, finally, how to integrate our sensors into a circuit we have learned. So, I will conduct this session in four parts. The first part will be of basics of sensors, where I will explain this parameters and introduction section. Then the next part I will introduce you to the physics of sensors, and then the next part will be fabrication and characterization, and finally I will talk about this like systems and circuits, how to integrate these sensors. Okay, so let's start. I have clubbed these two, the basics of sensors introduction and the parameter section within a single section. So, in the week 1 and 2, we have learned this. So, at first, we have learned what is the sensor. What is a sensor? Sensor is a device that measures a specific parameter and converts into a signal. So it can be any type of parameter, and it just converts it into a readable signal or a readable format. So not only this, it also converts it to a readable format. So I have given already examples of a speaker and microphones. Similar to that, like a transducer is a device that converts one form of energy to another. So a transducer changes one form of energy to another. So it can be from electrical energy to an acoustic energy. So, like in a speaker, which is a transducer, what happens? We give it electrical signals, and it converts to acoustic or sound signals. So this kind of a sound signals we can't detect directly, or we can't get a quantifying data from it. But what happens that we can hear the sounds directly through this. So this is a kind of a transducer. Whereas in a device which changes a specific parameter and converts it to a signal. So let's say it is a microphone. So what does a microphone do? Microphone changes acoustic signal, that is the specific parameter, we are giving that may be an acoustic parameter, and then converts it to a signal that is in a readable format. So it converts it into a electrical readable signal. So what happens here is that like after recording our song or something like that, with a microphone, you can directly like rehear it inside your phone or maybe laptops or those things. So this is the basic difference between a sensor, a transducer. So a sensor can be a transducer sometimes, while a transducer, like a transducer is not essentially a sensor only. So if it is in a like the output is in a readable format, then it's a sensor. While if it's like it can be readable or it can be like in a different kind of a media like acoustic media or those things, that is called a transducer. Now, based on the sensing principles, we can divide this kind of a sensors in several classes. Other than that, we can also divide these sensors based on physics involved. So based on the physics involved, we can directly directly divide these sensors into a thermal sensor, where based on the thermal principle we get any specific data like a temperature sensor or those things. Then there can be a mechanical sensor. By like a pressure or a mechanical force, we can get a specific data. Then based on the device architecture, there can be several type of sensor like NEMS, that is nano electromechanical sensors. The like what do I say like the parameters are in the nano range, so that's why these are called the NEMS or nano electromechanical sensors. Similarly, MEMS, that is micro electromechanical sensors, where the shapes are in what do I say like in the shape of like a micro range. Then there can be field effect transistor based sensors, where using a field effect transistor you may make a memory or those things, or a humidity sensor also. So using this, you can make this. Apart from this, based on the application, which is the most common one, that is it may be sensing some parameters from the environment directly. So it may be an environmental sensor. Similarly, if it's detecting any kind of a chemical substance or like a reaction from a chemical substance, it's a chemical sensor, or maybe a biochemical sensor or those things. Apart from this, it may be a physical sensor as well. So a physical sensor is detecting some physical parameters. So clearly you can see that these things like these classifications are like overlapping. So a mechanical sensor is obviously a physical sensor, because if you are discussing about a pressure sensor, let's say, what happens, we put a mechanical pressure on this, and because of that it's a mechanical sensor. The physics involved is mechanical pressure here. Similarly, based on the application, like it will be recording a physical value of my pressure, pressure from my hand or thumb or something like that. So that's also a physical sensor. Based on the substrate itself, it may be flexible and rigid. So if this is flexible, these things we use for like wearable technologies, where we need the sensor to be flexible, because otherwise we can't attach it directly to our hand or something. And for circuits and those things, it may be rigid as well. Apart from this, based on the dimensions, as I have already told, that based on the dimension, if the sensors are like in micro region, so it may be MEMS. Similarly, it may be in the nano region, so it may be called as the NEMS, based on the dimension only. Then based on the active material, if the sensor is made out of polymer material, we can say it's like a polymer based devices, whereas it can be directly on top of a silicon wafer or those things. So it will be it. Apart from this, so like a polymer one can also be a flexible one, while silicon one is mostly in rigid cases. So these everything is like overlapping. So based on a specific sensor or those things, we can directly characterize it as like, based on the physics involved, we can tell it as a thermal sensor, but it's sensing maybe an environmental parameter. Maybe it's sensing the temperature outside our room, so it will be environmental sensor, whereas it will be a thermal sensor as well. based on the states, like if we are giving a liquid liquid stimuli to our sensor for, like, let's say, pregnancy kit. So in a pregnancy kit we give samples of urine, right? So that is in liquid state. Similarly, like there is something solid, so it will be in a solid state based sensor. Based on the mechanism, like if we are directly measuring it, so what is a direct or indirect sensor, let's say. So if you have an input and if you have your sensor here and you are getting directly output which is directly in a readable format, right? So it is the direct sensor. Like let's say a direct temperature sensor which is just giving like the direct temperature data to you to read, or a specific like a processor to read. Apart from this there may be input. Here's a sensor, and then you need another sensor or another circuitry which will just convert your output here. It was it was in a readable format but not of our kind. It will convert it using a external circuitry to in a readable format to take the data out. Okay, to take the data out. So these kind of sensors are called indirect measurement sensors. Now, moving on to the next part, that based on the sensors, now basic things that these are the materials for sensor fabrication. So based on your application, you will have to choose the material very carefully. So based on the material, like if you want a flexible sensor, these are your choices like PDMS or PI, that is polyamide, or PVC, polyvinyl, polyvinyl. Uh, I don't remember the full form of PVC, but like PI is polyamide and those things. For rigid, it can be on like rigid silicon substrate, or it can be on top of any kind of a glass or those things. So based on your specific application, you have to fabricate these sensors using a silicon wafer maybe, or maybe a PI substrate or those things. Now based on the active material, so conductors can be made out of carbons as well, or even polymers as well. So polymer conductor may be P dot PSS. So by increasing the doping parameters inside a P dot, we can just convert it into a conductor itself. Apart from that, for like semiconductors, it can be IZO, indium zinc oxide, or different polymers can also behave like a semiconductor. So like it may be like something like DPP, DTT kind of a thing. C8, BTBT. There are several polymer semiconductors in this case, and or so some can be of like based on your specific use case. It may be solution processed or it may be thermally evaporated or those things. Now insulators can be specifically polymers, so like PVC, PVP, PVA, these kind of a polymers we can use. So what is the main reason to use this kind of a polymers is to induce flexibility inside your device. So if you are using, let's say, PVP as an insulator, semiconductor maybe, let's say, C8, BTBT or these kind of things. Conductor, let's say you are using very small kind of a conductors or carbon-based conductors. So what will happen that this thing is flexible, this thing is flexible, and this thing is flexible. So if you are using a substrate that is flexible, let's say PVC or PI, let's say anything. So if this one is also flexible, so your total device will be flexible as well. So that's the basic thing to like consider if you are specifically looking for a flexible sensor, or you are like you are fabricating the sensor for some wearable needs or those things. Now for electrode materials, we use metals that can be like what do I say, like maybe that can be gold, silver, platinum, this kind of a things. Apart from this, we can use different polymers as well. So these things, both of them are semiconductors as well as polymers. So based on the doping concentration inside polymers, we can like use them as an electrode or like polymer electrodes or polymer conductors. Similarly, we can use them as semiconductors as well. And for like several oxides like ITO, indium tin oxide, or FTO, we can use them as an electrode as well. So like we have to specifically choose our specific material based on our needs and based on our application as well. So there may be like let's say, let's give an example maybe. Just wait a second. So let's say you are working with 200 degrees centigrade temperature. So you need a temperature sensor which can sustain 200 degrees centigrade. So the first question is, do you need a flexible sensor or not? Do you need it or not? So if you need a flexible sensor, so your next question will be which kind of a substrate will you use? So there may be these options like PDMA, PVC, PI, these things. So like PVC may be the lowest cost among these. So you will be using PVC anyway. But whenever you are saying that you will be working above 200 or nearly 200, you will have to use a PI substrate, which is a bit costlier than PVC, but you have to use it anyways. Then next for like if you need a flexible one, the next question will be what kind of insulator do you need? So you can use any kind of insulators like PVC, PVP, and these things. So based on the cost and based on your specific application, you will have to choose this. Let's say you are choosing PVC or this thing. Then you have to specifically choose your semiconductor, then your conductor, and those things. Apart from this, there will be certain challenges with the environment as well. So, like, let's say you are using this sensor uh, on a ship. Okay, and where you know that the humidity is very high, so you are, let's say you are measuring any kind of a different parameter, and based on the humidity effects, the parameters may change or may not. Okay, so to negate this humidity, you may sometime encapsulate the sensor as well. What is encapsulation? So you will encapsulate, let's say this is your sensor, you will need to cover it using a different kind of a material which won't interact with your with your substances, and even with higher temperature or those things they won't react with the materials you have utilized to fabricate this sensor. Okay, so encapsulation works like this. So you can just directly keep the contact pads out if you're going to take the data of this sensor. So you can directly have the contact pads out, and you can directly take the data from the hair while you have already encapsulated inside a pouch which is humidity proof. Okay. So sometimes you have to specifically choose a material which is not, let's say this encapsulation is made out of PDMS. So you have to choose a material which will not react even at higher temperatures with PDMS as well. So these are the specific choice cases where you have to specifically choose the material. You have to specifically choose this material based on cost, based on your application, based on different structural layers which will react with this kind of a layer or those things. Even with higher temperature, several like constant layers shouldn't like react with each other. Okay. Now, now the main thing to learn is that our sensor parameters, how to characterize a sensor, that if the sensor is is good for your use case or not. So there are several parameters like 20 or something parameters, but out of those sorry, I have outlined these things. So the first question should that will arise in your mind is that how accurate is the sensor? if the sensor is accurate enough for your use case or not. So that is called the accuracy of your sensor. So if your sensor is accurate enough for your use case or not. Yeah, if you can use the sensor for a specific case or not. So accuracy is one of the most important parameters you have to look out for in a sensor. Then the next question will be how narrow the distribution of measurements are. So what does it mean? It means if your sensor is precise enough or not. That is the precision of your sensor. So if your sensor is precise enough or not, then we need to calibrate a sensor as well. So calibration is also necessary. We have to recalibrate based on our known values, and we'll get the our output value will be very nearby to our to our desired value of those things. Now, the next question should be how small a change a sensor is able to measure. If there is a very small change of let's say for a temperature sensor, there is a small change of 0.01 1 degree, 0.01 degree change. Our sensor, if if it's sensing for several let's say very important equipments that should not go beyond let's say 100 degree or 200 degree. So in those cases, in those use cases, you need a very sensitive sensor, right? You need a very sensitive sensor. While in normal cases, you can have a low sensitive sensor. Based on your use case, everything is depending. Now, minimum signal a sensor can detect. How minimum signal a sensor can detect? So that's called your threshold. That is that let's say we have a pressure sensor. Okay, a pressure sensor. Just a second. Yeah, let's say you have a pressure sensor of or let's take the same example like of a temperature sensor. So you need to sensor temperature, but your sensor is inactive within this range, 0 degree to 2 degree. If your temperature is above 2 degree, your sensor works. Otherwise, your sensor doesn't work. So you have a threshold of 2 degrees. So what happens that above 2 degree, even a very small change can be achieved if it is a if the sensor has a very high sensitivity value, but it is the it is the thing that after that value the sensor starts working. That is called the threshold that a minimum signal a sensor can detect. Then the next question should be without even giving any specific input or any specific applied input to your sensor, there is already an output. This is called the offset. So ideally, your sensor shouldn't have any kind of offset. The offset should be zero. While it's not always possible, there is a very small offset. Based on your application, you have to optimize the offset as well. Now, what is the working region of a sensor? In which range a sensor can work. So this is called as the working range or span of your sensor. So if your sensor is working from 0 degree to 10 degree, let's say, so your working range is 0 degree to 10 degree. Okay. If your sensor characteristic is linear, what does it mean? That this is termed as the linearity factor. So what happens that if your sensor is linear, then based on the input change, your output will be similarly changed. And if your sensor is not linear, so based on the input change, the output may be higher or maybe lower as well. The change in output, change in input should be change in output. So this is a linear sensor, obviously, and based on these changes, so if your sensor is not linear, there will be maybe higher change in the change of output or lower change in the change of output. Output is altered with the direction, so it is called the hysteresis effect. In most of the sensors, hysteresis is the bad thing because history is not required in a sensor. So if let's say if your temperature sensor is sensing from 0 degree to 100 degree, so there's a basic range of 0 degree to 100 degree, and within that range, if you're going from 0 degree, 20 degree is equally let's draw this maybe. So Let's say if you have a sensor here, okay. So what happens? You are starting from here, 0 degree, and you are measuring 100 degrees centigrade. Okay. So at here, let's say this is your 50 degree. Okay. And this is corresponding area is here. Okay. While you are coming back from 100 degree to 0 degree, let's say, maybe it will fall like this. So you are going this way and it is coming this way. So what will happen? That this point is corresponding to this. So let's say at even 10 degree, the values are same. So when 10 degree while going downwards, there is 10 degree is equals to 50 degree when going upwards. So this is a not like this you don't require a hysteresis in your sensor. Although in some cases or some specific use cases, you will use this hysteresis to your usage that maybe a memory inside a memory, hysteresis is necessary to store the data. Like in field effect transistor based memories, we utilize hysteresis to store the data and then to retrieve the data as well. Apart from this, there are several other parameters as well. So the next point is how selective a sensor is towards your target parameter. Let's say you are only measuring the temperature, but based on the humidity, your temperature is getting deviated or those things. So your sensor shouldn't have any deviation towards humidity if it's a temperature sensor. So this is called selectivity. A sensor should be highly selective in specifically electrochemical cases. Electromechanical and electrochemical sensors should have a very high selectivity. How repeatable a sensor is. So if you are measuring 20 degrees centigrade, let's say, so how many times does the value comes very nearby to 20? So this is called repeatability. Sensors become insensitive within a certain range. If the sensor is working, let's say from 0 degree to 100 degree, but about let's say 10 degree to 15 degree, the sensor is not changing its output. So it can happen for several sensors. So this is called as the dead band. So within your working region, there may be certain ranges where your sensor doesn't work at all. So this is called a dead band. Ideally, you should avoid a sensor with a dead band. But if your application doesn't, let's say you are only measuring from the temperatures of 60 degree to let's say 70 degree. So if a sensor is very sensor is of low cost and it doesn't go to this range of 10 to 15 degrees, so you doesn't need to purchase the more higher cost one, right? So you have to just purchase a sensor which have a dead band at 10 degree to 15 degree and it will be fine as well. Then the next one is amount of the smallest detectable change a sensor is able to detect. So how small of a change a sensor can detect? Very small change. So this is called the resolution. In everyday life, we generally use this kind of resolution thing. So resolution, it is called resolution. A smallest amount of detectable change in a sensor which is able to detect. How stable is your sensor? So how stable is our sensor? Like after how much time or how many cycles of reading data, our sensor is stable. So that is called the stability of our sensor. Unwanted fluctuation. So like if our sensor is getting getting triggered with unwanted fluctuations or not, so that is called the noise. We have to keep the noise margin in mind. Then electrical signal required for an active sensor. So this is called the excitation. So how much of electrical signal or let's say a battery is required to like run the sensor. Okay. Time a sensor takes to reach 90% of its maximum output. This is called the response time. So if we are giving, let's say, 20 degree to a temperature sensor, and it should give us the data back immediately, right? But there may be a certain time delay of it. Let's say of let's say 2 seconds. So if we are in our normal day-to-day thermometers, we can see that if we are if we are going to measure the temperature of our body, we need several minutes, like 1 minute or 2 minutes to it takes about 2 minutes to read the data from our body as well. So the response time in that case will be 2 seconds. So ideally, in like very time sensitive cases, we need a very responsive sensor where it will respond within a few microseconds, a few nanoseconds as well. Time a sensor takes to reach a 10% of its maximum output with no applied input. That is called the recovery time. So if you are so if you are measuring a certain amount of time or that kind of a thing, so what will happen that your sensor needs a specific time to get recovered. Okay. So you need a specific time to your sensor to recover, and then again take another data for a different case as well. So these are the parameters. Maybe yes. So this is everything from the first fractal. So I'll just repeat again. So I have already told you that is what is sensor, what is a transducer, what is the different among them. Based on different phenomena like physics involved, device architectures, and these kind of a things, we can classify these sensors in different parts. And these kind of a classification is overlapping in nature, right? Then sensors materials, what are different kind of materials, how to choose a separate material, and how our choices should be put that it shouldn't affect any other constitutional structure or constitutional layer within this sensor as well. Then sensor parameters, where we have learned about accuracy, precision, calibration, sensitivity, threshold, offset, working range of span, linearity, hysteresis. And here we have learned selectivity, repeatability, deadband, resolution, stability, noise, excitation, response time, and recovery time. So anyone has any question regarding this? The basics of sensors. Anyone has any questions? Please go ahead. Then I will move to the physics of sensors. If anyone has any question, I'll stop for 2 minutes and please ask any questions. If you have any issue with your microphone, you may type in the chat box as well. So no one has any questions? Mhm. So maybe we'll move to the next part. Yes, anyone have any questions? I guess not. Okay, so we'll move to the next part, right? So we have already learned about the basics of sensors. Now we'll learn about the physics of sensors based on different kind of physics, how to choose our sensors, and what are the physical phenomena that these kind of sensors follow, and these things. So in the third fractal, we have learned about the capacitive and thermal type of sensors. In the fourth fractal, we have learned about the chemical and impedimetric sensors. And in the fifth one, we have learned about the optical and magnetic sensors. Okay. So I have clubbed this three in a single fractal, and we'll just explain those. So as like I have like given examples of specific everyday life use cases or those things like advanced sensors. So I'll like move on with them as well. Sorry. Yes. The first one was like in week 3 we have learned about this. That is the capacitive sensors. So for capacitive sensors, we know the basic capacitive sensor is a parallel plate capacitor. This is a parallel plate capacitor. So a parallel plate capacitor may have some dielectric in between its two parallel plates. It may be like air, so the relativity constant will be epsilon naught, that is 8.854 something. And like there may be, based on this kind of a capacitor principles, we can even detect the displacement of this block or those kind of things. But one of the most advanced one is like our phones. So we use a phone with an capacitive touch sensor. Previously it was a resistive touch sensor, but nowadays we use a capacitive touch sensor. So what happens in this touch sensor is that our hand, so this is the metal plate and there is a dielectric block on top of it. So if our hands is on top of this, right, what will happen? The field will change from here to here if it's touch. Okay, let's say it's touched right now. So the field will change, and based on this, capacitance will rise or capacitance will decrease. So by this decrease and increase of this capacitance, we will be able to detect the touch, the pressure, how much amount of pressure we have given. Like as I am writing writing something on my phone or those kind of things, it will detect how many touches are there. So based on this, it may be in a like a grid kind of a structure where you will have multiple capacitors and sensors based on like how image can be divided into pixels. So like multiple capacitive sensors can be like attached together to form a structure like this. Like in our phones, we have multi-touch functions where even if we are touching, like even if we are trying to zoom something, so what do we do? So we use this pinch kind of a gesture, right? So we touch here and we touch here, and then we just like pinch it, or zoom in, zoom out. Those kind of things are done by this. So there is multi-touch sensors where like based on like your two touches, it will be able to detect that. And the basic touch sensor, sorry. So the basic architecture looks like this. We have a microcontroller here. Let's say this one is a P block and P2 block, right? Here we have a resistance. Here we have a capacitance. And here we have a touch sensor. Okay, so based on this change in capacitance, our microcontroller will detect the change in capacitance, and based on that, several functions will be performed. So this is a capacitive sensor where change in capacitance is the basis of this principle, where based on the change in capacitance in case of sensors, we detect as like several entities. Like we can make a displacement sensor out of a capacitive touch sensors, or capacitive sensors, and like capacitive touch sensors are one of the most daily used applications as well. Now, then the next topic is thermal sensors. So thermal sensors are sensors that can obviously detect thermal energy, that is temperature or those kind of things. So a thermistor This kind of a things are like everyday examples of this. But one of the most unique examples or real life examples are thermal vision cameras. So what can a thermal vision camera do? So a thermal vision camera can directly take photo of an animal in a very low light setting. So as it works in the NIR range, so like in IR there are several ranges. That is the near infrared region, there is the mid infrared region, and there is the far infrared region. So based on this NIR and MIR, so we can take the image and we can get the thermal value of thermal energy at a specific place. Let's say we have a block like this, and if let's say there's a leakage of thermal energy from this, there's a leakage of thermal energy from this point. Okay, so based on this area, we can get a direct image that, and these are the cool places, right? So what will happen based on this, we can say there is a issue with this IC, and the issue is here because this is the center point of your thermal, like a higher thermal point. So if your phone like this, let's say, if your phone like this, so if your phone is getting heated up here, so the main component which is getting the most heated up, so that is here. So based on these principles, like in marine ships or those kind of things, where they won't have any kind of engineer or those kind of things, they will use a thermal vision camera and they can detect where is the like water coming from. If let's say there's a hole inside the ship, and a freezing water is going inside it through that point, so obviously the temperature of that point will be the lowest of inside that image, right? So you can detect where the hole is. Similarly in a IC, if a specific component is getting heated up, you can directly detect if like which component is malfunctioning or like that. So thermal vision camera is one like daily life usage for capturing animals or like based on thermal vision. Similarly, it is being used in security reasons as well to detect security breaches or those kind of things. Okay, so let's really move to the chemical sensors. So what are chemical sensors, right? So chemical sensors are divided in like where we detect only based on the chemical reactions on top of the sensor. So there are physical reactive and chemical reactive. Physical reactive sensors change its shape. Like if it is a sensor based on the pressure applied on it, it may bend like this. So based on this bending, we can say it is a physically reactive sensor where based on some natural phenomena, those kind of a thing, it changes its physical shape. So change in physical shape. And chemically reactive sensors are that doesn't change its shape obviously, but the top surface reacts to the chemical reaction. If let's say there's humidity in the air or those kind of things. So based on the chemical reaction, we can say that there is no physical shape change, but we'll still get the data which we intend to get. Okay. And apart from that, there is the indirect and direct type. So I've already told this that direct type is that measures the data directly, whereas for indirect type, the data is not measured directly. Okay. Now we move on to the electrochemical sensors. What are electrochemical sensors? So based on the principle it works, there are several kind of electrochemical sensors. The first one is potentiometric sensor, which is based on the change in potential of a sensor. Change in potential of a sensor. So most common potentiometric sensors are the pH meters. Here it is a pH meter. Similarly, based on the change in current, the amperometric sensor. Change in current. So this is a gas sensor, which is the most common example of like amperometric sensors. And this is the conductometric sensor. That is, this one is ion sensor. Okay. So based on the conduction, we can conduction of what do I say, like based on the conduction through the sensor, we can directly detect ions inside. So through this channel, let's say here, if there are conductive particles here, what will happen? The conduction will increase, and based on that, we can say a specific kind of a ion is present there. Okay. Now there are different kind of sensors. So as I've already told, then we come to the optical sensors. What are optical sensors? Optical sensors are based on LEDs or lasers, and we detect it through a CMOS, a CCD, or a camera. The change in this optical signal detected using a CMOS or CCD or these kind of a things. So here, let's here. So we can discuss it directly. Yes. Okay. So here's a LED source which is giving the direct LED here. Based on this LED, the LED is going through this pinhole. So in every mouse, there's a pinhole right there. So apart from the mechanical mouses which were being used about several years ago or those things, but in optical mouses, what happens? There's a pinhole structure. This made out of lasers or LEDs. So lasers are like in like very high-end mouses, like gaming mouses and those kind of things. But LED is the most common one. So based on these mirror structures, the light is here shown on the surface, and based on the movement of your mouse, the reflected signal goes back directly through this line and is captured using a CMOS camera. Okay. So based on this change in position and change in everything, so based on this, we detect the change in position for a optical mouse based on our hand movement and based on everything. So what happens if we put the mouse on a like on a surface that doesn't give any kind of a reflection? So the mouse won't work at that kind of a surface. So one of the most used optical sensors are obviously like optical mouses nowadays. Then we move on to this. That is the magnetic sensors. So one of the most important magnetic sensors are metal detectors. What we get to see inside any kind of a shopping malls or like airports or those things. That is our metal detectors. So what happens with the metal detector? There's a EM field, directly created EM field, right? And if a metallic object is passed through that, because of that, there's an interference in the electric field, right? Because of this, there's an interference created inside the electric field, and this change in interference is captured by a microcontroller or a microprocessor or something. And based on this, we get the information there is a metal present. Similarly, RFID tag works, right? So what happens in RFID tag? There's an antenna which is just giving electromagnetic signals, and if RFID tag is what we say, the block the electromagnetic fields, it will interact and it will share its data to the antenna itself. So the RFID tag is getting energy from the antenna, whereas the antenna is getting information from the RFID tag, and through the reader we can directly read this data. So this is a basic principle of a magnetic sensor. Metal detectors are one of them, and RFID tag reading and those kind of things are another one. And the last one in this like different kind of a sensors or physics of sensors is the microfluidic sensors. So what is a microfluidic sensor? So it can be of pregnancy kit or any kind of a ELISA kit or something. We use it for dengue detection. So what happens inside a inside a microfluidic sensor is that we have a basic sample collection pad where we put several drops or a single drop of our like sample, or like you it may be urine, it may be blood, or like different in different cases, right? There's a absorption pad after that, absorption pad which will absorb this. There's a conjugate release pad which will release several conjugates that may be antibodies and those things. So there are two separate lines, right? The first one is known as the test line. What a test line does is that it detects the presence of a certain amount of like presence of certain ingredient inside your sample. So it may be blood glucose inside your blood. Okay. Yes. Also, this is a glucose detection kit. So blood glucose inside your blood. So if this test line works, that like it gives a positive result, that means your blood sample is enough to calculate glucose data from this. The next line is your control line. Okay, control line. So what happens in a control line there are if there are like if there are glucose inside your blood, or like if there's HCG, human chorionic gonadotropin hormone, that is the hormone that gives us the symbol that it may be a pregnancy. So it measures the presence of this kind of a hormones here, and the final one is the collection pad, which just collects the remaining sample inside this. So here, like it goes through a microfluidic channel. That's why it's called the microfluidic sensor. Okay. So based on this test line data and the control line data, we can verify if HCG is present in your urine, or like if blood glucose like of a certain amount is present inside your blood, or those things. So there can be also false positive cases. What it means that with any kind of abnormality, there can be rise of HCG. Okay, with rise of HCG, what will happen? That the pregnancy test kit will give you a positive results, right? But it's actually not true. So this is a false positive. Similarly, you can get a false negative as well. So what happens in a false negative? A false negative is kind of a let's say ectopic pregnancy or those kind of a things, that there's no increase in HCG as well. So HCG remains same, and your test will come out to be negative, but still there's a pregnancy. So this is a false negative and a false positive case. So multiple time tests are needed and multiple checking is needed. Even this kind of a sensors can be used for some use cases that is not intended. So like for cancer detection, we can use this, where uh, even in male body, we can use this pregnancy kits to know if there's any abnormality or something. If there will be abnormality or some kind of cancer or a lump or those kind of things, it will show that there is like a pregnancy. That doesn't mean he has any kind of a pregnancy. It may mean that he has some kind of a lump or those kind of a things. Cancer may be like forming in in inside his body. Okay, so this is it. This is it for the second part. So if anybody has any question, please let me know. Please go ahead and ask any questions. You can ask any kind of a question, no issues. I'm sorry. Yeah. Anybody has any questions? Until then, I will write the reasons. It may be of ectopic pregnancy, and it might be cancer or those kind of things. Okay. If anybody has any questions, please let me know. I'll give you let's take a minute. And if anybody has any kind of a question, please let me know. Maybe there is no questions, so we'll move to the next part. So we have learned about the basics of sensors. Then we have learned which kind of a sensor do we need to use and this kind of things, like how the sensors are working and these kind of things. Finally, we need to learn how to fabricate these sensors, right? How to create these sensors, how to pattern these sensors, how to deposit material or a specific pattern on top of a sensor and these kind of things. So we'll move deeper inside this. So at first we need to know what is a clean room, right? A clean room is a place where the main fabrication occurs. So, there are several classes of clean rooms. It can be of class 1, it can be of class 10, it can be a class 100, and these kind of things. Okay. And there are several ISO standards as well, ISO 6, ISO 7, and these kind of things. In normal lectures, I have already discussed this. But apart from this, what are the most important things to learn about a clean room is that the the major contaminant, we need to remove the contaminants at first. Okay, so first let me explain this why a contaminant removal is necessary. So let's say you are preparing a very small sensor that is in micrometer range, okay? And there's a small channel inside your sensor. There's a microfluidic channel, let's say, and this range is only a single micrometer. Okay. Now, if there are particles even of like zero point 0.5 micrometer, that are very minuscule particles, but if this is the channel, let's say, so if two particles are just back to back, it will just block your total passageway. So even with single two particles, it may block your passageway. Yes, obviously it's like a rare occurrence, but still it may block. So let's say if there are like particles of 500 micron, what will happen with your sensor? Your sensor won't work at all, right? So you need a clean room where you are free of contaminants, and the first point we need to know that the most biggest source of contaminant is our body itself. So we have to remove all the contaminants from our body. So before entering a clean room, there's always a room which is used to enter inside a clean room, and we have to wear some caps to to remove the contaminants from our hair and those kind of things. We need shoe covers, or several times we need to just wear a different kind of a shoe there. We need to use gloves. We need to use mask. Even like there are jumper suits or bunny suits, jumper suits or bunny suits to just protect the sensor from our body itself. We have several protective glasses, and there at the tacky mat, there is this tacky mat. Even like even with the shoe cover, or even with the newer kind of a newer kind of a shoes or newer cleaner shoes, there may be some contaminants remaining. So that's why there is a high vacuum flow of air inside a clean room, where the air comes from the top. It will remove all the particles from our body, and it will be sucked through a vent in below our feet. Okay. And similarly, the apparel removal guide is similar. So the way you have already done everything, like if you have put on the gloves first, then you have to remove the gloves first. Then you have, if you have use the eye mask, like what do I say, like um, glasses second, then you have to remove the glasses second. So these are the way you have to just if you have done 1, 2, 3, 4, 5, and you have to just remove them through 5, 4, 3, 2, 1, and these kind of a things. And there is always a single single entry inside to inside to a clean room, because single entry, and also it is used for exit as well. Okay. Because we need to keep the contaminants as low as possible, so a single entry ensures that the contaminants are very limited through that. So these are the basic things that we need to fabricate inside a clean room. Now there are several deposition techniques, that is the chemical vapor deposition, where chemical vapor deposition, where a vapor is chemically deposited on top of your substrate or on top of your sensor, let's say any constituent layers. Okay. So the most used cases are oxides, nitrides, some kind of metals, sulfides, and these things. Okay. PVD is the physical vapor deposition, where a physical vapor is directly deposited on top of your substrate. This is done by physically, just similarly like as we have already discussed in the previous case, right? Where was it? Yeah. So in chemical senses there was a physical one and a chemical one. The physical one changes the shape, and similarly here there is a physical one and a chemical one. So what happens here, just a second, yes. So what happens here, that like a several structures. So if let's say a structure is here and it is deposited on top of this. So there is a physical vapor deposition, whereas by a chemical reaction, it is deposited on top of it. Now, one of the most unique one is AND, that is atomic layer deposition. Although it's very slow, but it has the most precise deposition technique. So it doesn't have any kind of a cracks or any kind of mismatches or those kind of a things. So, and even we can change the temperature. So obviously for a chemical reaction to occur, we need a higher temperature, whereas for a physical deposition, we need a much lower temperature. We need a higher temperature, but that's much lower. So the growth mechanism is self-limiting. So we can deposit each layer of 1 angstrom, that is one atomic layer at a time. So based on this 1 angstrom, we can directly, what do you say, directly control the amount of deposition is necessary. So let's say we need a 50 nanometer deposition. So we can directly control if there is a deposition of 50 nanometer or more than that. Okay. And coverage is 100%. That was what I was saying, that there are no errors inside this kind of a deposition techniques. Okay. Now, one of the two of the most important fabrication or deposition techniques are thermal evaporation and sputtering. So what happens in a thermal evaporation is that there's a boat with a specific material inside it. It's called a boat. So this has a specific material inside it, crucible containing type metal, that is called a boat. Okay. So we have gold, maybe here we have gold or silver, and we just heat it. And this is everything is working in, like, let's say 10 to the power minus 6 torr pressure. So it is a very high vacuum, and inside this what we do is we heat this material, and by heating this material the material shoots directly towards upward, and there's like a substrate holder which contains our substrate or here. Okay. And there's a deposition of this gold or silver or those kind of things on top of this. So if we need a specific, let's say a specific design or something, so let's say if we want a design of this. Okay. So we'll just make a mask of this kind of a thing, and like based on this heating structure, this will only be deposited inside this structure. Okay. So this is called the thermal evaporation. So no, there are no self-induced defects. Um, There are no self-induced defects, but there may be defects due to, like this. Let's say, um, sorry, yeah. So let's say here, okay. So if your structure is like this, because of this, there may be shadow effects. So there is a lesser deposition in this area, while there's a higher deposition in this area, and this kind of a things may happen. And so because of that, there's an uneven deposition as well. So there are defects, but there are no self-induced defects here. Okay. Now, in the like the second technique, that is the sputtering technique, what happens that it's in a argon environment. Okay, in an argon environment, what happens that we give a high voltage to the source. Okay, what happens that this argon gas is sputtered towards a material that is our cathode, that is negatively charged. So what happens that by hitting this kind of, like, the argon atoms along with oxygen atoms directly hit this cathode, and what happens that hmm, several particles from this surface moves towards the top surface, and here with our substrate holder is our substrate. Okay. So this kind of like particles directly hit here, and they just gets deposited. It gets deposited. So what is the major issue with this is that, okay, so and also this is happening in a plasma environment as well. This is happening inside a plasma environment as well. Okay. Now, in this kind of a deposition, there may be defects which are self-induced. So previously these kind of defects were not there, but because of this heating, so like here is the M particle, right? So this M particle, what happens that it hits the substrate, and if let's say our substrate was like this, okay, so it will hit here. There may be self-induced defects, and this kind of particles will get deposited on top of this. So this is the major flaw of this. Although it happens in a very fast rate, and it gives you it gives you a better coverage, greater coverage than thermal technique. So what happens that as like it's getting faster and everything, so you can see that here is also deposition, right? But in thermal there is no chances of getting deposition here in these points. So what happens that it gives you a better coverage, although there may be some self-induced effects as well. Now, One of the most innovative technique you may say is sorry. One of the most innovative technique is ALD or atomic layer deposition. What happens in an atomic layer deposition is that the substrate is here. Maybe I'll draw this. So a substrate is here, right? And if you have a specific particle on top of the substrate, if you are purging something, let's say hafnium, HFOH, okay, hafnium oxide you are purging. So several particles of hafnium oxide will be connected with this, okay? And there are limited spaces where these hafnium particles may be connected with this. So these will get connected here, and after that, in the next step, what will happen? Will purge basic water. Okay, so with this purging of water along with nitrogen, what will happen? These connected particles will be here. These connected particles will be here. Although there will be several unconnected particles as well. Okay. By this kind of a purging of water, what will happen? This kind of a excess molecules will be removed from the area, while only the connected particles will be remain. Okay. In the second one, what will happen that in the second one with another purge of hafnium, with another purge of hafnium, there will be another atom on top of this. But similarly, with another purge of water, the excess will be get will get removed. Now, what happens with each step? There's a single atomic layer deposited. That's why it's called ALD, atomic layer deposition. So it's a very slow process. So even with let's say, even if you want to deposit a thickness of only 50 nanometer, it requires about 16 hours plus 5 to 6 hours of starting the apparatus, and it takes 16 hours to get fully deposited. Now you have the main control of the thickness. So you can control the thickness based on how much you want to deposit, or what do I say, like how much amount of this, let's say half name in this case, how much of half name you want to deposit, or what is the required thickness. If you require a 40 nanometer, you can directly get the exact 40 nanometer. Even if you want a 50 nanometer, you can get directly that. Even if you want 40.2 nanometer, let's say, you can directly get that as well. So this is the main USP of this kind of a technique, that is the atomic layer deposition. Which is not possible with thermal deposition or sputtering deposition techniques. Now, now we move on to the next part, that is our patterning part. Okay, so these were deposition techniques, and we have discussed the most used three ones, that is the ALD, the thermal deposition, and the sputtering techniques. Now we'll move towards the photolithography. So photolithography is the most used technique, where we have a clean substrate here, and on top of that substrate we have a metal layer. We have a metal layer deposited. Okay, a metal layer deposited on top of this substrate. Now, the first step is to process the substrate. How do we process the substrate? We try to clean this substrate using, let's say, nitrogen blue or something, or like maybe we preheat the substrate or these kind of a things. Now, in the second step, what we do is that we spin coat the photoresist. So there's a chemical called photoresist. And based on the nomenclature, with photon it may resist or it may melt away. Okay. So there are two types of resist. There is a PR that is positive and there's a PR that is negative. So we'll look into that later. And then what we do that there's a coating of this particle this brown colored one is the PR coating. The PR is spin coated completely. Now now there's the step that is called the soft baking. What happens in this case? In soft baking, we heat the substrate at a relatively lower temperature. At a relatively lower temperature we heat this, but what will happen that it will stabilize the amount of PR on top of this substrate. Okay. In the fourth step we expose UV lights. This is a UV light on top of this PR. So what will happen, we'll have a photomask. This is called a photomask, and it will have a specific pattern on it. Using this this kind of photomask will shine UV light source or maybe deep UV light source or those kind of light sources through this photomask, and depending on the pattern it will get exposed to several regions of that photoresist. Okay. So there are also two types of photomask as well. First one is a bright field, while the next one is a dark field. Okay. Next one is a dark field. So we'll explain those after this as well. So what happens after this is that there's a development process. So we just put this inside a solution named as the developer solution, and it will melt away the PR here. In these positions, it will melt away those PRs. Okay. Okay. So it will melt away those areas. Next, what we do is we do the hard baking process. So this is a relatively higher temperature. Okay. So at a relatively higher temperature, we hard bake or we heat this, and so the remaining PR gets settled down or gets stabilized. Okay. Now we do the etching process. The etching process can be of wet etching or it may be of dry etching as well. So will what will happen with etching process is that it will dissolve the PR very slowly, while it will dissolve the metal very fast. Okay, so here the metal will get dissolved with usage of this kind of a agent, and by this what will happen that there will be the pattern exactly copied directly onto the metal layer itself. Now the last one is that the reduction where we just or the stripping point strip the PR layer. Okay, so we'll strip the PR layer, we'll remove the PR layer, and the remaining one will be the patterned metal layer. Okay, the remaining one will be the patterned metal layer. Now, so this process is called the photolithography process, where based on the choice of PR and choice of photomask, you can determine what kind of a pattern will be there. So if you want a positive like a plus pattern, let's say, or maybe I'll change this. If you want a pattern like this, okay, with a positive PR you will get a pattern directly like this. Okay, while using a negative PR you will get a pattern that is negative to the pattern we have here. Okay, so we'll have a negative pattern here, like in like a previous kind of a real type of imaging, the like we used to have this kind of a negative images. So this is the negative image of the pattern we need. In bright field mask, the field is bright. Okay, so what does that mean? The total mask is made out of transparent material, while the signs are made out of the design are made out of opaque kind of a material. Okay, similarly in a dark field mask, the total mask is dark, where the design is only transparent. Sorry, that's yes. So in a bright field mask, what will happen that everything will be transparent, while the design will be opaque in nature. Okay. So based on usages and different applications, you may use a photo mask, different kind of photo mask and different kind of a PR. And this is the basic process of photolithography. Okay. Now, based on the fabrication and characterization techniques, there are several characterization techniques like AFM, SPM. That is, AFM is the atomic force microscopy. So these are the characterization techniques where you have a cantilever beam that is called the AFM sensor, and a direct laser is shine on back of this sensor, and we get this collected through a photodiode, and with while it's scanning, let's say like this, so there will be a shift in your sensor, and based on that there will be roughness recorded through this light sensitive part. So apart from this roughness, it can measure also height and these kind of a things. There is also another setup that is called SPM, and there are like three different modes of this kind of a AFM images. So the first one is the contact mode, where the tip is always in contact with the substrate here, as you can see. The next one is the non-contact mode, but it will be very nearby to the surface as well. This is called the non-contact mode, where the tip is not in contact with the surface itself. Okay, and the third one is the tapping mode, which is the most sophisticated mode, where the tip for some time it will touch your surface, and for some time it will be above, and then in the next instance it will touch your substrate as well. So what's the basic difference between this is that in non-contact mode the tip will get damaged along with your surface. So let's say damage, there will be surface sorry so there will be surface damage and also the tip damage. So if let's say it's like a organic or a polymer material, what will happen with the contact mode? The surface will get totally damaged, and you won't get the data, and also your sample will be destroyed. Okay. In non-contact mode, there is no damage to the surface and also no damage to the tip. But there's another issue that is with the accuracy. So in non-contact mode, the accuracy is very low. Accuracy and precision both, right? And in tapping mode type of thing, what happens that there's a surface damage, a very low surface damage. The tip damage is also very low, while the accuracy is good. Like not very high, but still it's like in a like usable range. So it is also another different kind of a thing where we tend to use the tapping mode for like more softer cases where we have the metals. We can use the contact mode, also the tapping mode as well. There are several kind of a microscopy techniques where just a second. Yes, there are several kind of microscopy techniques. One of the most common one is the optical microscopy, to using like a visible light. So the main problem with the optical microscopy is that it requires a visible light. So it has a limitation that up to a certain limit of resolution, it won't go any further. And also with a certain let's say what do I say? Like there's a certain limitation of numerical aperture as well, so you can't make a huge numerical aperture as well. Okay. Apart from this, there is also electron microscopy where we use electron sources. So electron sources can be of type of thermal electron sources or electron emission guns. So based on different electron sources, we may use them for microscopy purposes. TIM and SIM are the two techniques we use for this kind of a thing. So for electronic microscopy, it has a much higher resolution and much higher atomic. We can go inside an atom and directly see the atomic structure as well using this. So there is also another terminology that is called HRTIM, high resolution TIM. So here we can say that SIM and TIM, SIM is for 2D imaging only, and TIM is for 2D imaging only as well. So TIM, while it may have 3D imaging, but still it's not directly 3D imaging, right? And SIM can't have a like 3D structure. AFM is also it's scanning through every line. Okay, so if you have a like this, so you have to scan multiple times. So by using that, you like logically you may have a 3D, but it's not essentially a 3D image. It's a 2D image that you have rearranged to look like a 3D image. Okay. So this was the third portion. So if you have any kind of a question you may ask, then I will move on to the last part, that is the sensor systems and circuits. I'll just take a sorry. Yes, I'll just take a break for a minute and then I'll come back. If you have any questions, please let me know. So, anyone have any question? I guess yes. I just okay. So we'll move towards the last fractal. That is the sensor systems and circuits. So we'll learn about the sensor, how to use this fabricated and like design sensors inside a system or maybe inside a circuit. Okay. Yeah. So the first thing we need to know is the signal conditioning circuit. What are signal conditioning circuits and how do they work or those kind of things. So a signal conditioning circuit is a block where you have this input, okay? You have this sensor and then you have this processor or those kind of things, okay? Or let's say maybe no. Or let's say you have a, like a output device or something like this. Like let's say a screen or something, and you can get the output. So it should work, right? But the problem is that it won't work in real life. What's the problem with this is that you need to first condition your signal before giving it to an output device. So if you have a sensor here, right, you need another block that is called the sensor conditioning circuit. Then you can give this value to a output device and it will give you the output. It will work perfectly fine. So what what are the things we need to know from this, right? The main thing to know is that a sensor, like a signal conditioning circuit, not a sensor, this will be a signal conditioning circuit, sorry. But a signal conditioning circuit may be of different types. So, based on this, you may need a buffer circuit, which will just isolate your sensor from the output device directly. Maybe there will be a impedance mismatch or those kind of a things. Then there will be a circuit that is amplifier. So in most of the cases, the signal directly obtained from a sensor may be in milliampere range, and you may need to at least have a ampere range, or maybe it's in a nanoampere range, and you may need to at least be in a milliampere range. So to change this like value or change this order of the signal, you need an amplifier. Okay. So what will happen in this case that not only the signal, your noises will also get amplified. Now, to remove this kind of a noises to be getting amplified, we need a filter to remove the noises. That's it. So these three are the building blocks of a signal conditioning circuit. That is the buffer, that is the amplifier, and also the filter. Okay. So there are several basic circuits. Like in the previous class, I have already discussed. So that's why I have just directly wrote that down here first. So the first one is a voltage divider circuit. A voltage divider circuit is nothing but two resistors attached in a series, where like across the R2 resistance we get the V out, and while we just put the V in here, and we can just replace any of the resistors with a resistive type sensor, and based on this we get the current through the circuit is V in by RT, right? And RT is the total resistance, that is R1 plus R2, and voltage drop across the V out or the V2 is nothing but VIN R2 by R1 plus R2. Okay. Apart from this, the major flaw with this is that is environmental degradation. So this resistance can change with maybe humidity or maybe temperature, those kind of things. So to like correct this circuit, which can withstand maybe heats or humidity, we'll use a circuit that is called the Wheatstone bridge. what happens in a Wheatstone bridge is like that we have two separate voltage divider circuits here. The first one is a voltage divider circuit, the second one is also a voltage divider circuit. And based on this, we can find that at this point VA, the value will be this, and based on that, the value at this point is VB. So if the bridge is in a balanced condition, there will be a galvanometer connected in between, and it should show a value of a zero voltage. So for a balanced condition, the equation turns out to be R1 by R2. Okay, so I have written here R1 by R2 equals to R3 by R4. This is the condition for a balanced bridge. Okay, and based on this, we'll have a sorry, just let me move it to here. Yeah, so based on this, we'll have a value of this. So this is the bridge balancing condition. Okay, now. So, apart from this basic circuits, we have several kind of amplifiers. So, one of the most used amplifier is operational amplifier. That is IC741. One of the most used kind of amplifier is IC741 or an operation amplifier. So based on this operational amplifier, it looks like this. Okay. It has two terminals, a negative and a positive. It has two supply terminals where you have to put the supply to turn it on. You get the output from here and you just give the input first V in one and this is V in two. Okay. This is V out. So this is a basic op-amp structure. So why is it called an operational amplifier? That is the main question, because it can do several operations using this. We can do several operations. Basic operations like summing or differentiating. This can be done. Apart from this, it is also an amplifier, so it will anyway like amplify your signal. So the basic two configurations are the inverting amplifier, in which we just put a resistance here, and this is a minus, this is a plus, and it will go towards the ground. Okay, and we put a resistance here and we get the output from here. So this is V2 and this is V1. Let's say this is resistance 1 and this is the feedback resistance RF. So I am not going to derivate it today because in the last class I've already discussed. You can check it out from YouTube itself. But the value of V2, or let's say V out, is nothing but minus RF by R1 multiplied by V1, or minus RF by R1 multiplied with V in. So the gain factor is A equals to minus RF by R1. So there's a negative gain. That's why it's called an inverting amplifier. Similarly, another most common structure is non-inverting amplifier. So what happens in a non-inverting amplifier is that we put this we put the source, that is V1, directly to the non-inverting terminal of this, and we put a resistance here. We just directly put it to the ground. Okay. Here, from here, we will have a resistance which will just connect here, and let's say it is RF. This is R1 and this is V2. So for this case, we get the value of V2 equals to 1 plus RF by R1 into V1. So in this case, the gain, this is the inverting gain and this is the non-inverting gain, equals to 1 plus RF by R1. So there is no inversion in this case. That's why it's called a non-inverting amplifier. Based on this inverting amplifier, we can have several resistances here. So like several resistances, and based on this factor, we can say we can use it as like if all the resistances are same, let's say R1, so we can find out that it is a summing amplifier as well. So we can use it as well as a summing amplifier. Similarly, there are different configurations for differentiation, integration, and those kind of a things, and we can do everything using that, using a capacitor in the structure. So these are the simple structures where we use only resistances, but in several cases we can use a capacitor and we can directly get that. Now, apart from these things, we have the filters remaining. Okay, so what are the different kind of filters? So based on the, if you know where your noise is like situated, like let's say if you have a signal from 0 to 1 gigahertz, okay, and you know exactly that my noises are in like a few megahertz, so like in range of few in sorry, let's remove this. You have that it's inside of few megahertz. Okay, so what do you need is a high pass filter. So what is a high pass filter? High pass filter is a, like you have a lower cutoff frequency here and it goes towards this. Okay, so this is the view, that is the frequency, and this is the output. So what will happen that it will block all the lower frequency noises in this range, and it will only just pass the higher frequency signal. Similarly, there can be a low pass filter where you just need to pass this region, that is the higher cutoff frequency, and based on this you can just get the signal directly from this, and there may be like higher frequency noises as well. Apart from this, there are the band pass filters where you can directly pass a specific band. So if you know your like signals are directly here to remove the repels or like those things, so it may be F1 and F2, and you can directly signify them that your signal is only in this region. Apart from this region, no region is more important. So that's why you can use a band pass filter. And finally, you can have a band reject filter where you know the noise is in this region, so you may block that region. So a band reject filter is like this. So there is a band reject filter where you can reject a specific band to work. Where in low pass filter you reject the high frequency noises, in high pass filter you reject the low frequency noises, and in band pass filter you reject the high and low frequency both type of noises, and you just pass the signal which is like you know a specific frequency region from where this happens. Okay, now another thing to discuss is that apart from an operation amplifier, one of the most used one is an instrumentation amplifier. So that is also an important structure we need to learn. Okay. So this is the basic course structure. So I have completed today's one. So if anybody has any kind of a question, please like let me know, and I will try to explain this. But this is the 8 fractals of this course. The first 2 fractals were basics of sensors, where we learned the basics of the sensors. What are sensors? How are the sensors utilized, requirements of a sensor, that is the basic parameters we need to know for our specific requirements, and this kind of a things. Then in the next portion we learned about the physics of sensors, like a capacitive sensor, what is a capacitive sensor, and those kind of things, or a inductive sensor and these kind of things, resistive sensors and all those things. So what kind of a sensor do we need and how these sensors work? Okay, working principle. In the last portion here, we have learned about how to fabricate these sensors using like PVD deposition techniques, CVD deposition techniques, ALD deposition techniques, or those kind of a things, and how to pattern those like lithography techniques, how to pattern these sensors, lithography techniques, and these things, how to etch your sensor. Then finally, how to characterize your sensors. Okay, I'll change the color maybe. How to characterize your sensors. Okay, characterize your sensors. Like if you need to know the roughness of your sensors, you may use AFM. And for the optical properties, which I have not like touched on this lecture, so there may be Raman spectroscopy, there may be UV spectroscopy, there may be XRD. In XRD, you use the diffraction of a light through a material. In UVS, you use the UV and visual range absorption spectra, while in Raman, you use the Raman scattering effect to determine the specific like knowledge for the specific material. To know more about the atomic structure of the material, you need an XRD, while for the absorption statistics and for the band gap statistics, you need an UV spectra. And then finally, we learned about how to characterize this using AFM or SPM and these kind of things, and then its optical characteristics. And finally, here in the last part where the sensor and systems and circuits, we know how to integrate our sensors and what are the signal conditioning and why do we need it. Okay. So this is the basic course structure. After this thing, so like you may know how the sensors work. You may choose the sensor directly from the market, or you may like to fabricate the sensors. You can also characterize the sensors, that how the sensors work and how specifically a sensor can be put to work on those kind of things, and the fabrication procedure should be happen in a like a clean room, and like what are the measurements you have to take, and what the exact materials you have to choose. So I missed that. So what are the exact materials if you want it to be flexible, or you want it to be rigid, or those kind of things. And finally, how to integrate this sensors using a signal conditioning circuit, maybe using an instrumentation amplifier, or maybe using a instrumentation amplifier, or maybe using an op amp basically, so directly, or even using a wine bridge, Wheatstone bridge structure. So how to utilize this sensors inside your system, and how to utilize the sensors or connect the sensors with external circuitry. So these are the things we have learned from this course, and thank you for attending the session. Please ask any of the questions you have. I'll like to answer them. Anybody have any question you may ask? Yeah, Sumit, you wanted to ask something? Okay, I don't think anybody has any questions. So then we'll end the session here.
Sir,
Yeah, yeah, yeah. Yeah, go ahead.
in assignment number one,
Hmm.
there was a question. Just a second.
Yeah.
What is the principle of active transducer?
Okay.
The principle of transducer is energy conversion, correct?
Yes. From one form of energy
But
to another. Yeah.
in the answer, I have take that only energy conversion, but the uh, valuation shows that it is load pressure.
The
In
answer was
assignment
what?
number
The answer,
load pressure.
load pressure.
Yeah, there were four options.
Yes.
First is load pressure. Second is energy dissipation.
Can you
Third
show
is
me? Can you
energy.
show me the screenshot right now? Then I may ask the NPTEL team to just look into it, because like if it's a wrong answer corrected, and like there may be something issue with that. You may like show me the screenshot or those kind of thing. Can you show that?
Yes, sir. Just a
Yes,
second.
yes, please show me that,
Um,
and then I will just like ask them.
can I post it in the chat?
Yeah, yeah, sure, sure, sure. Go ahead.
Just
Yeah,
locating
fine.
the chat. I'm not able to paste that particular screenshot to the chat.
Um, like, can you share your screen? Then, like, I'll stop sharing my screen, and you may share the screen, and then I can just take a look at
Sure,
it.
sure, sorry.
Yeah. So please go ahead and share your screen. Wait a second. I'll just stop sharing my screen. Yes.
So are you able to see the screen now?
Yes, yes, yes. Which
So
of the
the
following is
question number
the
three.
working? Yes, which of the following is the working principle of active type transducers? Energy conversion. Yes. Load pressure. Okay. Energy dissipation. Obviously not. None of the above. And load pressure. Ah, okay, okay. Let me take a screenshot. Wait a second. Okay. Mm, let me just take a screenshot and just yeah. So I've taken a screenshot and I will share it with them. And let's say you will get
But
resolved.
uh,
Yeah.
there is again one problem with the uh, assignment only.
Okay.
Uh,
Yes.
in week number two, I guess. I'm just
Yes.
checking.
So
Mm,
let me write it down somewhere. Week one, question number three,
three.
and week two,
Uh,
and week two,
uh,
question number.
no, sir. I'm just checking. Just a second. I
Yeah,
just
yeah, fine, fine. Yeah, fine.
in question number seven.
Okay. Yes, yes,
Uh,
yes.
so in question number seven also, I have marked the correct option only, but the score is reflecting as zero.
Can you just share your screen at that position?
Uh, yes, sir, sure.
Yes, please share your screen, and then I may attach that screenshot as well.
See now.
Yes, yes.
So in question number seven here, the
So
answer is
is it is in week what?
week again same week number two, sir. Week two only.
Oh, okay, okay, fine. Yes.
Question number
So
seven is option is correct, but
okay,
score is
it's a technical glitch, I guess. So no worries about it. I will just tell them to correct this. Okay, and I'll share these issues with the team. Okay.
okay,
Anything more?
correct.
Anything more?
Uh, no, sir. No.
Okay, okay, fine, fine. Okay, I'll ask them about these two problems, and then I guess they will solve it. Okay.
If there is any problem, so actually I have just viewed only two assignments just now, and I found
Hmm.
these problems. So
Okay.
if I get some more problems, so where can I
Like you
go?
may directly mail me, right? You can directly mail me, and then I'll forward that to them.
It is your mail ID from where you can give it.
My mail ID is I'm writing in the chat box. Okay.
Sure.
Can you see this?
Yes, sir.
Yeah. You can just copy it,
Mhm.
and if you have any kind of a problem, then you can directly mail me, and uh, then like I'll forward them the issue. Okay.
Yes, sir.
Yeah. Thank you.
Okay.
Thank you for
Thank you
attending
so
the
much,
session,
sir.
and I guess you will get like this solved. Okay. Fine.